speed and the power consumption. Is it clear? Any question? Yeah.
You said that the first part, you only have to worry about the size for the first part just because the delay is longer than each of the other segments?
You were talking about this?
Yeah, so what's like the middle section looks similar to that, but you don't worry about the sizing for the middle.
Yeah, because the probability of these transistors being used is only two data patterns. For 6 data patterns, it goes either this way or that way, right?
What about like the next part before the sum? Yeah.
This one?
Yeah.
This one, the thing is that if you look at the main purpose, I really don't care how fast this is generated, because I have to still wait for this signal to come to get the actual value. So why am I going to chew up all my power here to making the transistor bigger? You follow my point?
Yeah.
That's the rationale. So this is going to be my sizing for balanced design in a very elementary way. But a good circuit designer will do the data pattern analysis and he'll say that, hey, look, these transistors are going to be used more, so I'm going to increase all of them by a factor of 2. These are going to be used less, these are going to be used less, so I'll just make them the minimum size transistors. Believe it or not, this is a good design. Okay? I'm just giving an example with a mirror adder, but this will be your rationale of design for everything. Yes?
What do you mean they'll be used like less? Like less as in, like you said, the sum part will be used less?
Oh, this one?
Yeah. What does that mean? Like you mean that it will
The size of the transistors are the smallest size, so the power consumption will be minimum. See, the power consumption is proportional to the input capacitance, right? So if the size of the transistor is small, the input capacitance is small.
I'm
Correct?
saying how do you know to prioritize
How to choose this value, right?
Yeah.
Select it. Because here the sum is, as he asked, I gave you the answer that if you look at the adder chain, the sum is generated over here. Now, I do not have any good reason to make this transistor larger size, because even if this sum is generated early, I cannot read still the results until it goes all the way there, right? Make sense? So now going back to this, NMOS, PMOS chains are completely symmetrical, maximum of 2 series transistors in carry generation circuitry. When laying out cell, most critical issue is minimizing capacitance at node C0. Reduction of diffusion capacitances is particularly important. Okay, let me just read out and then I'll explain. Capacitance node C0 is composed of 4 diffusion capacitances, 2 internal gate, blah, blah, blah. Transistor connected to Ci are placed closest to the output. Only transistors in carry stage have to be optimized for optimal speed. All transistors in some stage can be minimum sizes. Okay. So this is what I explained. Now, one thing I did not explain is, am I going to put Ci here or here? The recommendation is that the carry input will be closest to the output. Similarly here, the carry out, which is generating this, will be closest to the output. What is the reason for that? Yeah.
Because carry in is complicated, so A and B is ready far before CIs, right?
A and B has already come there, right? So all the internal node capacitances and all those things have been charged, discharged, and all, right? So as soon as this comes, boom, this generates, right? If I put this at the bottom and put A and B over here, then again the charge sharing and all those problems will be coming actually, right? So that's one thing. Another thing is that later on we'll see this is simple circuit. When you have a stack of PMOS, NMOS transistors, you have to size them differently. The diffusion capacitance of this should be the minimum because that's on the carry path. So this should be the minimum size transistors, and this should be on the closest to the output to basically take care of the internal node capacitances and all, the charging them and all. So always keep in mind, these transistors should be designed very carefully so that the signal propagation delay is minimized in this path. And second is that amongst all the signals, the signal which comes at the end should be on the top. This is the first and foremost principle of designing. It doesn't matter whether it is a carry or something else. Any signal which is generated at the end should be on the top, because that way you can maximize the performance of the circuit. So these are the things you have to keep in mind. Now I have already talked about this. I have talked about this one also. I talked about this also. Now this is another way to show the ripple carry adder, how we can 16-bit adder we can represent. So basically it shows that the ripple, in the worst case delay, the carry in value will be propagating all the way over here. So the delay associated with the carry in is equal to the carry, the propagation delay of this, then here this to the OR gate, and then through the n minus 1 AND OR gate. So this is just to, I mean, in your textbook they have represented it this way. It's not very difficult. Only thing is that they just write in terms of these symbols. The symbols are pretty straightforward. The concept is the same as I mentioned actually. So in the case of a 16-bit adder, when you are adding F in hexadecimal with 0, 0, 0, 1, then the carry, or rather you can do it another way. You can add with 0 and then you change the carry in from 0 to 1. So that means this will be changing from 0 to 1. In this case, the carry out will be rippling all the way from input. And that rippling delay will be 4-bit here, 4-bit here, 4-bit here, 4-bit here. So 16 minus 1, 15. Then the delay associated with these gates, which is called AO. Sorry. Delay of AND OR gate. So that is the delay corresponding to this part over here. Then we have to set up the function, the propagate function over here. So that is the delay corresponding to TPG. So this plus the T XOR functions that we are generating here, or rather TPG is equal to maximum of sure takes more time between these two functions and functions or XOR function, that is TPG. And then at the output we have the exclusive OR. So this is what the expression for ripple carry adder. Is it okay? All of you are okay with this? So now your life is a little more difficult than just making the adder. You have to also combine the logic function. Addition function, you can make the ripple carry adder, but then you have to also include the AND or an exclusive OR logic function. So in order to do that, there are many ways you can do it. This is there probably in your handout. Have all of you read this one? This one? You guys understand this? Isn't it there in your handout? This circuitry? No, not my handout.